including running the field campaign and be in charge of all the people who got sick. She had to be the resident like rescue person. That was part of why I thought was an exciting reason to recruit Emma. She came to the University of Washington in fall of 2023 with a Futures Rivers Fellowship. And this year she got a VALA Fellowship and moved from Washington to Norway. She's done work with both myself and Dr. Nicoleta Cristea. And today I will let her take over and present what she's doing with mapping snow cover at fine resolution in complex and forested terrain.
Great, thank you, Jessica. So, yeah, exactly what she just said. I'll be talking about mapping snow cover at fine resolution in complex and forested terrain. This will be my master's work that I'm explaining, and my committee members are Jessica Lundquist and Nicoleta Cristea, and along with them, my other co-authors on this work are Justin Flug and Kahan Yang. And I want to say thank you to the VALA program and also the Future Rivers program for funding. And to start, I'm just gonna get right into it. The study location for this work is actually a big motivation behind what we did. So I'm just going to talk about why Bud Creek Basin is relevant for this work and go from there. So we have Bud Creek Basin. It's located in Yosemite National Park in California. Bud Creek basin is mostly made up of exposed granite, and it has about 33% forest cover. In the basin, there's Bud Lake at 3,080 meters, and this is the source of Bud Creek. This is a relatively small basin, only about 7.6 kilometers squared, but this Bud Creek is very vital for Tuolumne Meadows, which is one of the largest subalpine meadows in the Sierra Nevada, and it's a prominent tourist destination. The Tuolumne Meadows has a very diverse ecosystem, and its groundwater levels are directly related to discharge from tributaries coming from the hillsides surrounding it. And so Bud Creek is one of those tributaries. Of the tributaries, Bud Creek is one of the smaller ones, but it actually maintains the longest discharge in the season. So it really helps sustain keeping those groundwater levels high. And Bud Creek has been gauged since 2001. Typically Bud Creek will actually have stream flow until August, while the other tributaries might not. And because of this exposed granite that I had mentioned, a lot of the water, the runoff from Bud Basin is direct runoff. It's not really interacting too much with soils and subsurface flow. But why is Bud Creek maintaining this long discharge if it's a small basin? Well, Bud Basin's pretty complex terrain, and we can look at right here. This is the slope, the surface slope of a 3-meter digital elevation model of Bud Creek or Bud Basin, and we can look and say like, oh, what are these blue lines? Like, what's this purple? Well, how is this contributing to the basin? And these lines right here are actually really deep, narrow fissures that snow will accumulate in, along with these deep depressions. And so throughout the winter, snow will end up in these piles, and then they're shaded from solar radiation, and wind redistribution, and it kind of acts as like this self-refrigerating snow piles that last longer, and they sustain that late season stream flow with Bud Creek that's really important for the meadow and the ecosystem downstream. And so, yeah, if we care about these meadows and the stream flow, we should also care about the snow. Specifically, how much snow do we have in the basin? How much snow cover is still there? And how do we quantify this? We can use satellites. There's a long, rich history of using optical satellites to measure snow cover. And one of the most popular methods to do this is snow cover products from MODIS remote sensing instrument. And so we'll look at today this spatially and temporally complete MODIS snow covered area product. It's around 500-meter resolution, but it's a daily product. And it's spatially corrected for forests and temporally corrected for like degraded images or cloud coverage. And so if we look at this product, we see, okay, this looks a little bit different. Like, what are we looking at, Emma? This does not look like the bud basing you just showed us. Well, this is what bud looks like through the eyes of coarse resolution satellite. So you're actually not getting so many pixels within the basin. And it's difficult to really capture those narrow fissures or small depressions that we saw pictures of earlier. And then also, if we care about late season stream flow, we care about late season snow piles, and this coarse resolution product is actually saying that we have no snow following June 27th, but we know that stream flow is lasting till about August in the basin. So there must be snow up there somewhere because it's not interacting with soils so much. It's more of a direct runoff. There's still snow in the basin. And so something to note, optical satellites can't see through trees. So they often miss snow in the forest. And that's why I mentioned that this STC mod scag product is spatially corrected in the forest to address for that limitation. And this post-processing accounts for the fraction of vegetation in each of these pixels. And so if we want to see these really heterogeneous snow piles that like gather in these deep fissures, we can use LiDAR as one way to do this. It's laser altimetry, light detection and ranging. And so this product can actually show snow in these fissures. It's a snow depth product, and you can see these dark blue lines in the far left graph. And then you can convert that to a binary product if you want. And so it can say for each pixel in this 3-meter pixels, is it snow or no snow? And LiDAR is not affected by canopy like optical satellites, but unfortunately, it's expensive and it's only in select basins and repeat flights. There's usually only 1 or 2 following April 1st, which in this work, we look at April 1st to the end of the water year. So which is through September. And so we can use 3-meter resolution satellite imagery, which from the LiDAR, we know that 3 meters is sufficient to see really high accuracy. So if we have these optical satellites, here is a PlanetScope image. PlanetScope constellation is 3-meter optical satellite imagery, but it has near daily resolution. So you're not limited by the repeat flights, say LiDAR has, but you still have that high resolution. And so this is a commercial product, but it's been available since 2016. And the way that you can use optical satellites to detect snow cover is that on Earth's surface, different surface types have certain reflectance values for given wavelengths in the electromagnetic spectrum. And so in this bottom left chart, we can see the dashed lines show a typical trend for what you would see a spectral signature for snow on the ground. And so if we have these reflectance values from a satellite, we can put them into a model to determine whether there's snow or not. With this PlanetScope constellation, they have 4 to 8 reflectance bands available and 3 generations of sensors on board of them. And so I just want to note here, it will be relevant later, but if we look at these different channels that the instruments are have, you can see this first generation of sensors. They overlap each other quite a bit, and we have the red, green, blue, and near infrared is the brown wavelengths. And then in the second generation, there's a bit more separation between these different channels. And then we have this third generation that mirrors the second generation pretty well. They just have some additional bands. And so something to consider with this imagery is PlanetScope is subject to some issues with saturation when you have bright surfaces. Sometimes it can cause the saturation and blooming, where you can see this bright green and the blue in this far left snow map or map. And then in the middle, we have this haze kind of coming through, and that's a cloud that's interfering with the capturing the surface reflectance. And then also PlanetScope imagery like that coarser resolution, spatially and temporally complete mod SCAG product. It also has issues with detecting snow in the canopy. And so I just want to start with some work that what I'll talk about that is part of my master's thesis builds off of some relevant work, and some of it I might go into depth, but just hang on with me because it's all relevant, and a lot of these methods they add on to each other. And so to start, we'll be talking about Yang et al. 2023 using high resolution mapping of snow cover and mountain meadows and forests using planet imagery and machine learning. So in this work, Yang et al. Trains a random forest model, which is a relatively simple machine learning model, which I mentioned. If we have our reflectance values, we need a model to identify or determine if there's snow cover. And so how Yang et al. Does this is they use these LiDAR snow depth maps, these really high resolution, 3 meter, and turn those snow depth maps into snow cover maps. And so then when you find a corresponding PlanetScope image with a date for a given LiDAR flight, you can actually match up that snow or no snow label to the 4 different bands or reflectance values that we had looked at that those sensors can capture. And so you feed a model the training label and then the corresponding reflectance values. And then your model can then be used to identify snow or no snow in other PlanetScope images. And so the methods from this work moving forward will be referred to as Yang et al. And in this work, Yang et al. Used 3 binary performance metrics to evaluate their model. And I'll just briefly go over them, but I'll also use them further in my work. So we have precision, which is used to measure commission in a model. So is your model overestimating snow? Usually lower precision means a higher commission. So in that case, your model would be over predicting snow. Um, and then we have recall, which is used to measure omission. And a lower recall means a higher omission error, which means that your model is missing some snow and it's under identifying snow. And the F1 score is a good score to kind of um, understand how well your model is doing, because it balances those two measurements and it uses the harmonic mean to calculate it. And so it's also works okay for imbalanced data sets. Say if you had a snow map that was mostly snow covered, the F1 score can handle that. And so Yang et al., although it was developed for these meadows, they actually tested it in forests and found that as you get closer to the canopy edge, and once you are in the canopy clusters, the model performs worse. And once you're in the open, it has better performance. And so they kind of clumped these different distances into categories and tested different categories and how the model performed. So from this work, we know that using PlanetScope in machine learning, there's some disadvantages, which is identifying snow in forest clusters and maybe small gaps in the forest. And then additional work that was performed is using commercial satellite imagery to reconstruct 3-meter and daily spring snow water equivalent. And this is Flug et al. 2024. I won't go into detail about the reconstructing snow water equivalent because that's something in itself. But to do that, Flug et al. Also used this random forest model that was developed in Yang et al. For snow mapping. And instead of using LiDAR flights to train the model, Flug et al. Manually labeled pixels snow, no snow, or unobserved. This introduces a third class where you might have these saturated images, or you could have a cloud interfering, or just part of your basin wasn't in the field of view of the sensor. And so they actually do this on multiple images. So this way, the model is exposed to a wider range of reflectance values and might be able to handle different image quality conditions. And moving forward, the training methods in this paper are referred to as Flug et al. And additionally in this work, Flug et al. Used a temporal post-processing, which temporal post-processing has been used in other snow cover products. But essentially how it works is, say you have a snow map on May 18th, you also have on May 19th, that looks all right. May 20th is like, it's saying all snow everywhere, but it's not true. And you look at the imagery and it's actually a cloud that's mistaken for snow. And then, back to the next day, May 21st, and it looks normal again. So this post-processing will adjust that map that was either affected by a cloud or maybe saturation, and can correct those pixels. And they also determined that you can use PlanetScope snow maps to determine the date of snow disappearance within 3 days of uncertainty. So you can figure out when the snow disappears at the end of the season, which is really important for the work that I'm going to talk about that's relevant for sub-basin hydrology and ecology. And so what have we learned so far? Yang et al. Uses this simple random forest model and trains it on one LiDAR flight and a corresponding planet scope image. In that work, they determine that model performance goes down when you're in and next to trees. And then Flug et al. Trains the model on several images and also manually trains them. So you're not limited by when do you have a LiDAR flight to use training labels. And this work also used this temporal post-processing to adjust for any fluctuations in snow cover. And then also that planet can be used for identifying the date of snow disappearance. And so our work continues the efforts to map snow cover at high resolution. And in this, we train and test model configurations. The two model training methods I just talked about, the Yang et al. Method and the Flug et al. Method, and then one additional training method, which I'll refer to as the composite method. And then we apply spatial and temporal post-processing using neighborhood statistics. And then we compare against a coarser resolution snow cover product that's available daily. In this work, we ask the following questions. Can spatial and temporal post-processing methods using neighborhood statistics improve high resolution snow mapping? And what model training method can derive the most accurate snow maps? And how does the moderately coarse spatially and temporally complete mod-scag fraction of snow covered area product compared to these fine resolution spatially temporally adjusted snow maps? And so to get into the new training method that we use, similar to Yang et al., where you use LiDAR for your training labels. In this method, we also use LiDAR, but we train the model in all of the open pixels, and then we train another model in all of the canopy pixels. So the idea is that each model is introduced to a narrower range of reflectance values for each category. And so in the canopy, you might see these darker pixels that are mixed pixels or pixels that are experience some shading from nearby trees. And then in the open, there might be a bit more brighter pixels. But we take both of these trained models and we apply them to planet scope images to map the snow cover. And here you can see this like green gray line in the planet scope image. That's where we would apply this canopy model. And then where you see this like brown orange color, that's where the open model would be applied. So you're stitching these two models together. And then to get into the post-processing techniques that we use spatial and temporal adjustments, and the temporal adjustments follow the methods from Flug et al. And we apply these temporal adjustments to all the pixels in the basin. And this will really account for when your model encounters these saturated pixels or cloud coverage or just missed scenes that aren't fully observed by the satellite. And then for the spatial component, this is the new component that we have developed. It's using a 2D convolution to incorporate neighborhood statistics to adjust pixels in the canopy. And so we go back to previous work in literature, and Yang et al. Had identified that in medium-sized forest gaps, the planet's it does pretty well identifying snow cover. And so we want to exploit the fact that Planet can see in these medium-sized gaps and spatially smooth out the snow cover so that extrapolate the information. And the way that this 2D convolution works is you have a neighborhood of pixels that your convolution will look at, and there's a source pixel in the middle, and so within that neighborhood that's defined by your radius size that you set, how many pixels within the neighborhood have snow. And so you also set this threshold. If you say, oh, I need 60% of the pixels in the neighborhood to have snow, to adjust this source pixel to go from no snow to snow. So this convolution moves across your image, and we only apply it in the canopy pixels. So it's not applied to the open pixels. And so in using this and testing our question one, which is, can spatial and temporal post-processing improve these maps? We wanted to figure out, okay, so yes, like we can use this spatial and temporal post-processing, but what makes the most sense for our neighborhood size and this threshold of required pixels? And so we use this F1 score that I talked about with Yang et al. And we tested a combination of different radius sizes for our neighborhood and thresholds to determine the most optimal one. In this work, we figured out that the radius size doesn't play too much of a role into how well the model does, but the threshold does. And the more stringent you are, that higher threshold, the model will put less snow in the canopy. And so because to begin with, these snow maps don't have a ton of snow in the canopy, the model will do worse, but still better than not post-processed. And we can see that the threshold has a bigger role in these images that have lower snow cover to begin with. So if we compare to these April dates, the range from the highest to lowest F1 score is smaller than our range for this May 18th date, which spans a bigger F1 score. And so because the radius size we're unclear which was the best to pick, we looked at our basin and we thought about, okay, with the density of our canopy, like how big are these forest gaps that we might actually capture if there really is snow in the forest. And so we used a radius of 3 moving forward, which also matched up with Yang et al. Results, saying that medium-sized forest gaps, the model performs well, and 3 pixels was the smaller end of that medium range. And so question 1, can this post-processing improve our maps? As you can see here, we'll go from left to right. We have our planet scope image, and then Yang et al. Map, which is that simple trained on one LiDAR flight. And then we have this post-processed version of the Yang et al. Map. And then we can compare it to LiDAR, which is our evaluation data set. And here we can see in this area where there's pretty dense dark canopy, the post-processing does add some snow in the canopy, and it gets it closer to what the LiDAR flight is saying. And so we can look at other dates in this May 18th date that maybe had less snow cover. We're still adding a bit more snow in the canopy, but it's less effective than when there was a lot of snow to begin with. And on to question 2, what model training methods had the most accurate maps? So we use this F1 score again, and we can see all the models do pretty well in open pixels, and in the canopy, they perform a bit worse. But these first two models, the Flug et al. And the Yang et al., they had poor to okay performance. But then the composite and the post-processed actually had, they had decent performance, and it was pretty reliable. And then we want to check in another year. In 2023 was a significantly like higher snow year in the basin, and the model still did good in the open pixels. And the canopy pixels were similar results. Maybe the post-process method performed a bit lower, but that could just be because it was trained in 2022 and tested in 2023. But we felt it was relevant to look at how our models do across the different sensors, because we know PlanetScope has 3 different generations of sensors on board. And so we tested the F1 scores for the 3 different sensors, and it was evident that when we used the model on the first generation of sensors, the performance wasn't as well as when we use it in the later 2 generations. And that makes sense. As we looked at earlier, the channels overlap each other for the first generation, and in the second, or the later 2 generations, they compare a bit more, and there's more separation in between these bands. And also, something else to note, the Flug et al. Method was the only training method to do better in a sensor that it wasn't trained with. And so I think this goes to show that when you train on multiple images, your model is exposed to different conditions of reflectance values, and maybe different image quality conditions. And so this Flug et al. Method can actually handle encountering a different sensor a little bit better. And then, how does our fine resolution basin FSCA compare to a coarse resolution? In order to make this a fair comparison, we resampled our fine resolution product to match the coarse resolution. And so here is an example of this. We have our PlanetScope image, our snow map that's post-processed from that, and then we downsample to match the resolution of our coarse spatially and temporally complete ModScag on the far right. And then we look at the basin mean FSCA throughout the season. For 2022, we are looking at the basin FSCA for our fine resolution product, and then our basin FSCA for the coarse resolution product. And when you see data points above the 1-to-1 line, that's saying that PlanetScope's actually saying that there's more snow in the basin than what the ModScag ModScag is saying, and also lighter is saying higher if it's a diamond data point. And so in general, they match the 1-to-1 line fairly well. Within the 40 to 80 range, it deviates a little bit, and ModScag is identifying a bit more snow, which is interesting. And then, but if we care about this late season snow cover, which is the point, we want to be able to identify these snow piles that are critical for the meadows. We can see in the very bottom, there's a stack of pink to orange, maybe some green pixels, and that's Planet identifying low snow conditions. So from that 0 to 7.5% of snow cover, Planet is reporting a range of different snow cover fractions in the basin, and then MODIS can't identify anything in between 0 and 7.5. So if you care about that last 8%, 7.5% of snow in the basin, maybe Planet is a better option. And so then we decided, let's look at 2023 again. We're missing a few data points. in the middle of the season due to filtering out like really highly saturated or degraded images. But again, there is a pretty good trend on the one-to-one line, and but you can see here at the very low snow conditions, Planet is identifying about 5% more snow cover than Mod Skag is. And if we want to look at our data, take a step back and look at what's the snow cover throughout the season. We have our LiDARs, these gray dots. That's our truth data set, or as close as we can get to the truth. And the Yang et al. Is the simple random forest model that we talked about. And so you might be wondering, like, what are this dip in the beginning of the season? That's what it would look like when you have these saturated images and your model can't handle that. And so it can really throw off what your model is saying is snow and no snow. And again, at the end of the season, we might be thinking, oh, wow, there was a big storm randomly. And no, that's just a cloud and it's bright. And our model can't handle differentiating between clouds and snow. And so then if we go through, we can look at the Flug et al. Method. And also it has these sporadic fluctuations in snow cover. And then if we look at the composite method, this one has a little bit more snow cover in the beginning of the season, which is encouraging. And it means that we're adding our model is identifying a bit more snow in the forest, which was the idea behind the composite model and why we trained one model in the forest and one in the open. We really wanted to get as much information from those darker forest snow pixels as we could. And then here we have the post-processed time series. And this just shows the importance of temporally smoothing your data, and no longer do we have these random spikes and dips in snow cover. And it matches the LiDAR pretty well on the dates that LiDAR is available. And then we have the coarse resolution, spatially and temporally complete Mod Skag, and they match pretty well. I would say the coarser resolution product identifies a bit more snow, again in that 40 to 80 range that we talked about. And this is all of our time series together. And if we care about the end of the season, these late snow piles, we can look at when the snow disappears. And so our course product is actually saying that snow disappears about a month earlier than our fine resolution product, which would, which in that case, it's not showing these late season snow piles that are important for the meadow. And so what does a planet image look like when Mod Skag is saying that there's no snow on the basin? We can see those where those blue and purple lines were earlier in the beginning of this presentation, where those fissures are. They still have some snow, and then also in these depressions higher up in the basin, they have snow, and that's the snow that's critical for this late stream flow that keeps the meadow wet. And to conclude and just go over our 3 questions, can spatial and temporal post-processing using neighborhood statistics improve high resolution snow mapping? Yes, it especially in the early season, it adds snow, and maybe later in the season a little bit less snow, but it's still adding snow in the canopy when we know there is still snow there. And then question 2, what model training methods derive the most accurate snow maps for snow open and under the canopy? I think it depends. the composite worked the best for trees without post-processing, but the sensor type does matter. So maybe trying some combination of the composite method with the fluidol method where you can expose your model to several image conditions might be helpful. And then question 3, how does fine resolution basin FSCA compared to coarse resolution? For the most part, they followed that one-to-one line, and so they compare pretty well, except for that last 8%, which we see this planet scope image has bright snow features when ModScag is saying there's no snow left. So yeah, that's the end. We found out that in this work we can actually use planet scope imagery to identify those late season snow piles, and spatially and temporal post-processing can help. And I want to thank everyone who's helped me along this journey to come to that conclusion. So thank you to my committee members, Jessica and Nicoleta. You've been so much help, and the co-authors on this work, and the previous work you've done has been great to add on to Justin and Kahan, and to the Mountain Hydrology Research Group. You guys are such good support. My family, and then the Treehouse grad students and the Fishbowl, and anyone else that I missed. But thank you. Any questions?
Just to clarify, we will take questions from everybody in the audience right now, and then Emma will go to another Zoom room with her committee for follow-up, like more difficult questions. But right now, would anyone in the audience either feel free to type it in chat and I'll read it, or just unmute yourself and ask. Okay, Stephen Pastana has a question. How do you think your post-processed composite method could be fine-tuned, such as picking a threshold percentage or radius for a different basin without LiDAR snow observations?
So I think, well, one thing that I think is relevant for this post-processing, and how we had tested that different combination of a radius and threshold. I think if you're applying any post-processing to a different basin, I would still assess that radius and threshold, and you could have a basin that has like a less dense canopy coverage than Bud Basin, and you might be able to get away with a bigger neighborhood size and a lower threshold. If you don't have LiDAR to test this, makes it a bit more difficult. But yeah, you could maybe try a basin that either has a certain, like a snow data, like if there's a snow pillow or a weather station, maybe you can at least get some information for certain pixels through that. But I would test different radius and thresholds. I wouldn't just go with what we used in Bud Basin, because all forests are different. Yeah, I don't know if that answers your question.
Yeah, you've got a question from Justin.
Okay.
Hey, Emma. That was really nice. Thanks for the really nice presentation. I really liked how you brought it back to the beginning with the late season snow persistence there. That's so important for Bud. That was really cool to see. I guess I had two small questions. I think the first is you kind of showed that slide where you showed better performance for the first generation of the PlanetScope sensor for the method. I was kind of curious, is that when you do the classification alone? Yeah, this one. When you do the classification alone using these different approaches, or does the Flug et al. In this case have the benefit of that temporal post-processing also that could get
No.
noise?
Yeah, no. So in all of this work, maybe I should have explained this a little bit more, but the only maps that we applied this post-processing to is the like most simple, this base model of the Yang et al. Method. So if anywhere where it says Flug et al., it doesn't have any post-processing added to it. So in that case, I think it could, if you tried the Flug et al. With a post-processing, it could add an additional benefit. And same with the question Stephen had. I'm not sure if you also thought that the composite had this post-processing like tagged on to it, but the composite is just that model training method alone. It doesn't have any post-processing. So yeah.
Cool. Okay. Yeah, that's really cool to see. And I guess my other small question was maybe related to Steven's a bit. And you might have said this and I just missed it, so apologies if you did. But what sort of stability do you think you have with this, composite approach in time? So for instance, Stephen was kind of asking about like the transferability to a different basin for your model. But say you have, planet scope in 3 years, but you don't have it in the fourth. Do you think your model could be extended forward in time and still work similarly?
I think, well, we did test it in 3 different years, and the post-processing method did okay. But one thing that I've considered is not just in time in terms of through different years, but throughout the season is maybe one threshold appropriate to have for a really high snow cover image versus a lower snow cover image. And so that might be something to consider, having one static threshold. Is that appropriate through time within the season? But from year to year, I mean, our model still did pretty well with these earlier generation acquisition or sensors, and this figure right here are actually from 2022. So the model was trained in 2023, all of these, or 2022, all of these models were trained, but then we tested 2020 with these 2 other sensors, and then 2023 as well. And I would say the biggest issue was having a different sensor, especially the first generation.
Sure. Okay, cool. Thank you.
Any other questions? All right, I'm not seeing anything in the chat or any hands raised. So let's go ahead and give them a big round of applause, which on Zoom is always not satisfying. We'll try to clap loud enough for everybody. And then Emma, take a 10-minute break, and at 10 o'clock, we'll reconvene on a different Zoom link. I'll send it to you in Slack, okay?
Okay, great. Thank you.
All right, I'll see you in 10 minutes. Stand up, stretch,
Thanks.
or run in a circle. All right.
Thanks, everyone.
Bye. Thank you, everyone, for coming.